This is Catherine Nightingale with Chattanooga State Community College, and this video is for Linear Algebra Section 6.2 on the topic of orthogonal sets. An orthogonal set is a set in which each possible pair of vectors is orthogonal. Recall from the previous section that two vectors are orthogonal if and only if their dot product is 0. So we'll be using dot products to test whether sets are orthogonal or not. The diagram here shows one example in R3 of three orthogonal vectors. You can see that u1, u2, and u3 all go off in different directions, but they all make 90-degree angles with each other. So u1 and u2, u1 and u3, and u2 and u3 all make 90-degree angles. We're going to do a few practice problems now on testing whether a set is orthogonal. So here's three vectors, u, v, and w, and we want to know if they form an orthogonal set or not. So what we have to do is we have to test every possible pair. So first let's list out the possible pairs. We have u dot v, u dot w, and v dot w. Anytime you have exactly three vectors, you'll have exactly three pairs to test. Okay, now let's do u dot v. Recall that we do first entries multiplied plus second entries multiplied together plus third entries multiplied together, and so on. So I'm going to do the 5 times -4, -4 times 1, 0 times -3, and 3 times 8, and add them all together, and I get 0. Okay, now I have u dot w. I'm going to do the same thing, first entries, second entries, third entries, and fourth entries multiplied together and added. Okay, so I have 5 times 3, -4 times 3, 0 times 5, 3 times -1, add them all together and I get 0. Okay, my third pair, v dot w, I'll still do the same thing, first entry, second entry, third entry, and fourth entry. So I will have -4 times 3 plus 1 times 3 plus -3 times 5 plus 8 times -1. When I add all those together, I get -32. And since this is not equal to 0, the set is not orthogonal. So even though u was orthogonal to both v and w, because v and w were not orthogonal to each other, the set is not orthogonal. So every single one has to be 0. Every single dot product has to be 0, that is, in order for the set to be orthogonal. Here's another example with vectors u, v, and w, and we want to test whether it's an orthogonal set. Now if you would like to, you can pause the video here and test yourself, and then come back and we'll work through the problem together. Now if you pause the video, you'll have seen the dot product of u dot v, u dot w, and v dot w. I'll start with u dot v. I do first entries, so 1 times 0, -2 times 1, 1 times 2, add them all together and I get 0. u dot w, I'll have 1 times -5 plus -2 times -2 plus 1 times 1 equals 0. And v dot w also gives me a dot product of 0. So since all possible pairs are orthogonal to each other, this is an orthogonal set. So I had to get 0 for every single dot product. Okay, now I'm going to give you a couple theorems. These are theorems from the book, Theorem 4 and Theorem 5. Theorem 4 states that any orthogonal set S that does not contain the 0 vector is linearly independent. So any orthogonal set that does not contain the zero vector is linearly independent. So because of this, S, if it's an orthogonal set, is a basis for the subspace of Rn spanned by the vectors of S. Okay, so let's just do a quick recall of basis. To be a basis, you have to have two criteria. One is linearly independent vectors, so meaning your set has to be linearly independent. And the second criteria is that you have to span the subspace. So because an orthogonal set is automatically linearly independent, we've met the first criteria. And it will, of course, span the subspace that's spanned by those vectors. So it will be a basis. Okay, so that's very important. Now we have Theorem 5. Let U1, U2, all the way through UP be an orthogonal basis for some subspace W of Rn, and let vector Y be an arbitrary vector in W. Then, because the U's are the basis for W, I can write Y as a scalar times U1 plus a scalar times U2, and keep going, plus a scalar times UP. Because you can write any vector in W as a linear combination of the basis vectors. That's something we discussed earlier in the term. And then the scalars, this theorem tells us how to find the C scalars. So C sub j is equal to y dot u sub j over u sub j dot u sub j. So that's the important part of the theorem, is that it tells us how to find those scalars. And this is for j 1 through p, so for every single scalar. Okay, here's a quick proof of Theorem 5. We'll start with the assumption of the proof. U1 through UP is an orthogonal basis for a subspace W of Rn, and Y is an arbitrary vector in W. Then because you can write any vector in W as a linear combination of the basis vectors, we can write Y as C1U1 plus C2U2 plus dot 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 plus CPUP for some scalars C1 through CP. Okay, to find a formula for the scalar C sub j, I'm going to dot both sides of the equation with the vector u sub j. So whatever I do to one side of the equation, I do to the other side, just like any linear equation. So I have y dot u sub j equals that whole linear combination dotted with u sub j. Now what we'll do is we'll distribute, and when we distribute, all the dot products are 0 except for u sub j dot u sub j. And the reason for this is u sub j is orthogonal to all the vectors in the basis except itself. That was one of our assumptions. So I'm going to distribute the u sub j here. And then this is 0. All of these are 0 except for the u sub j dot u sub j. So on the next slide I'm going to write what I have. So this leaves us with y dot u sub j equals c sub j times u sub j dot u sub j. And we can divide both sides by u sub j dot u sub j and get the formula for the scalar. Okay, so that's a quick proof of Theorem 5. And the thing that we use this for is projection, and you'll see that in the next video. For now, let's just do a quick application of the theorems so you see how they work. First, we want to show that U1, U2, and U3 form an orthogonal basis for R3, and then express the given vector x as a linear combination of the U vectors. Okay, here we go. So to show that they're an orthogonal basis, I'm going to do dot products. So u1 dot u2, I do 3 times 2 plus negative 3 times 2 plus 0 times negative 1. So first entry is multiplied plus second entry is multiplied plus third entry is multiplied. I get 0. Perfect. I'm hoping the other two end up 0 also. So u sub 1 dot u sub 3, first entry is multiplied plus second entry is multiplied plus third entry is multiplied, give me 0. Same thing for u2 dot u3. And I get 0 for that one also. So now, all zeros. So u1, u2, u3 is an orthogonal basis, or it's an orthogonal set. Now let's discuss a little bit why that would prove that it's a basis for R3. Okay, since u1, u2, u3 is an orthogonal set, the vectors are linearly independent. And that's by Theorem 4. That was one of the theorems we just went over. And then we have this, this rule from earlier in the term that any 3 linearly independent vectors in R3 form a basis for R3. And so we have 3 linearly independent vectors by Theorem 4. So from that rule from earlier in the term, we know that they form a basis for R3. So we've shown that they're an orthogonal basis for R3. So now we can use Theorem 5 since we have an orthogonal basis. So u1, u2, u3 is an orthogonal basis for R3. Now let's use Theorem 5 in order to actually find the scalars. Okay, find the linear combination of basis vectors that gives us x. So we know that x can be written as a linear combination of the basis vectors of R3. So x equals c1 u1 plus c2 u2 plus c3 u3. Now we also have the fact that c sub j equals x dot u sub j over u sub j dot u sub j. So that's Theorem 5 that we just went over. So I'm going to use that. I'm going to say c1 equals x dot u1 over u1 dot u1. So I'm going to do the dot products of x dot u1. So 5 times 3 times plus negative 3 times negative 3 plus 1 times 0 over u1 dot u1. So 3 squared plus negative 3 squared plus 0 squared. I get 24 over 18, and I always want to simplify. So 4/3 is C1. I'm going to do the same thing for C2. X dot U2 over U2 dot U2. Okay, I'll let you try this out. And we get 3 over 9, which simplifies down to 1/3. Okay, same thing for C3. X dot U3 over U3 dot U3. So x dot U3 over U3 dot U3 equals 6 over 18, which simplifies to 1/3. So I have all of my scalars C. Okay. Now I'm just rewriting x is a linear combination of the basis vectors. And I have my C1, C2, and C3. C1 was 4/3, C2 was 1/3, C3 was 1/3. And now I can check to make sure I actually get x. So I'm going to do 4/3 times vector u plus 1/3 times vector u2 plus 1/3 times vector u3. So I get 4 plus 2/3 plus 1/3, negative 4 plus 2/3 plus 1/3, and 0 minus 1/3 plus 4/3 gives me vector x. So the linear combination checked out, and I know that I did the scalars correctly. So that is how we apply theorems 4 and 5. Theorem 4 lets us test whether an orthogonal set is a basis, and theorem 5 lets us find the scalars in the linear combination of basis vectors.